What's up, guys? This guy again? Really? This guy again? Mr. Fortin? Are we off from this guy for like 9 days? What the heck? Anyways, Mr. Fortin here, filming another homework examples video for you, the students, to enjoy at some point during the next week. Again, these videos are optional, but hey, some of these questions are confusing, and sometimes you just don't want to wait until that Jamboard that we'll do on Monday when we get back to get a little feedback on this. Okay, so here are the problems that we're going to do together today. We got classroom exercises number 10, written exercises number 6, 8, 20, and 28. So we'll do a few of these here and get it going, okay? So anyway, section 3-4, we just introduced that on Friday. Make sure you watch the lesson video. The lesson video is pretty sweet. Already gotten some questions about that lesson video as well. Well worth your time to watch it. Again, you get about an hour and a half. You got that 47-minute lesson video, and then work on these homework problems for about 40 minutes or so. And then what's optional right now is to watch this. Watch my explanation, okay? So what this section had to do with was the isosceles triangle theorems. That's right. Before this section, really the only thing we knew to do with isosceles triangles was to use the definition of isosceles triangles, okay? So again, in the world, we identify what something is, we say what it is, and that's a definition. And sometimes definitions allow us to say other things in proofs, for instance, like establish other things in proofs by using that definition. So anyways, we have the definition of isosceles triangle, which again, an isosceles triangle, you're an isosceles triangle if and only if you have at least two congruent sides. That's it. That's all what the isosceles triangle definition says. It's a triangle that has at least two congruent sides, okay? And that's it, right? There's nothing more. There's no fact. There's nothing else beyond that. That is purely defined by the triangle. The only thing we know, if we have triangle ABC, for instance, okay, and then ABC, and BC, and AB were congruent, that's all we can say, right? That's an isosceles triangle. Boom, we have two congruent sides. We're good to go. Beyond that, so built beyond that, were the isosceles triangle theorems. We have the ITT, which is the main theorem of this section, right? The isosceles triangle theorem. That's if, right, you have two sides of a triangle that are congruent, then you're going to know that the base angles will also be congruent, or the angles that are opposite the two congruent sides. Or if you have three congruent sides, right, all three of the angles are going to be congruent. That's a corollary here, okay? So reminder, you have 6 new theorems, 4 of which are corollaries. Remember, corollaries are theorems as well. They're just theorems that follow very simply from the main theorems here, okay? You got the isosceles triangle theorem, and then you have the isosceles triangle theorem converse, right? Converse. So we can abbreviate those. The isosceles triangle theorem is abbreviated the ITT, and then the converse ITT is written as CITTT. So, sorry, CITT. So converse isosceles triangle theorem. Okay, so what the converse is, of course, again, you watch the lesson video, you're just like, Mr. Fortin, I want to jam away on some problems here. Converse ITT, that's not when you start with congruent sides, it's when you start with congruent angles, right? If I know I have a triangle with 2 angles congruent, then I will know that that triangle is isosceles because those sides opposite, right? Sides opposite those angles got to be congruent. Got to be congruent here. Here you start, this is the ITT, you start with congruent sides, you get opposite angles congruent here. Converse ITT, right? You get, start with the congruent angles, you get congruent sides afterwards, okay? So we'll practice this. We'll practice this next week as well. But what we're going to get into right now is classroom exercises number 10, okay? So I'm going to cross out these other ones here because you have to actually justify a bunch of the other theorems during this section. That's part of your homework here, okay? Because remember, these are 2 of the theorems. Is the ITT, right? ITT is one, the main theorem of the section. Start with congruent sides of a triangle. You know those base angles are congruent. The converse ITT is right here. And then these theorems have corollaries. They have things that follow from them, okay? So in problem number 11, you're going to explain how corollary 2 follows from corollary 1. And so this, you're going to have to use a textbook. Okay, so just a little background on this, you use a textbook. Hopefully you read the section, right? Read the section. This theorem here, we're going to call it the ITT, right? Isosceles triangle theorem, we'll call that the ITT. And then these corollaries on top of that, you got to memorize these. You got to know these. You got to be able to pull these out to defend future arguments that you're going to do, right? As you prove new theorems, prove new facts here, okay? So corollary 1 is an equilateral triangle is also equiangular. We're going to explain that together. That'll be one of my examples here today. And then for question number 11, you'll have to justify where this comes from, how you know this is true. Why does it follow from corollary 1, right? Logic, common sense. But you're going to have to use evidence in your convincing arguments, right, to see how it follows here. Corollary 3, you're also going to justify. You're going to justify corollary 3 in problem number 13 here. Explain why corollary 3 is true. Well, you're going to use this diagram that you have here from the isosceles triangle theorem, theorem 3.1. Use that diagram. You should be able to explain why you would know corollary 3 is true. We've talked about the proof of that a couple times now, because this is very similar to question number 18 on your section 3.3 homework, okay? Anywho, let's go ahead and get into it. I want to also remind you that these problems here aren't all the problems you have to do for your homework, okay? So reminder that we have our geo schedule that's linked to in Google Classroom. Feel free to pull this up whenever you want to figure out what the homework is. You just need to scroll down to where the date is. And so the last date was like Friday, November 20th, I think. Get into advanced math here. Oh, wait, there's Mr. Fortin. What's he doing there? I scrolled too far. That handsome devil. All right, let's, what is going on here? Jeez, where is this? Okay, so after it gets ugly, why is my internet being so crazy? This is nuts. Okay, section 3.4. All right, so here it is. Just to remind you here, the ones that I'm going to go over today aren't all the problems that you got to do. So you got to do all the classroom exercises, right? Number 1 through 8, 10 through 13. We'll do number 10 together. And I've already talked about kind of what to do on 11 through 13, so hopefully that makes sense. Hopefully you figured out, you cracked the code. And then we're going to do 6, 20, 6, 8, 20, and 28. So we're doing kind of a decent amount of the written exercises, but also note you got to do number 5, right? I'm skipping over number 5. We're not going to do that. We'll do 6 as an example here. All right, let's do this, guys. I know you haven't done geometry for maybe a little while. It's been a few days, or maybe you're checking your answers. A lot of people have actually turning in their homework already. That's pretty cool. Did their homework, and then they can forget about the stuff for like a little over a week, which is nice. Relax. It's just sweet. I love Thanksgiving break. It's so nice. All right. Well, let's see here. I've been blabbering on for, what do we got here? 7 minutes already. We're finally going to get into it. Okay, so we're going to do number 10, which says explain how corollary 1 follows from theorem 3.1. So let's check it out here. We might have to compare these two here. Corollary 1, that's the one that says an equilateral triangle is also equiangular. Okay, also equiangular. Why is that a proof? Why is that a theorem? How does that follow? So a corollary should follow directly from the theorem that got proved immediately before it. And in your textbook, they talk about proving this one before it, which is the isosceles triangle theorem. Isosceles triangle theorem is if two sides of any triangle are congruent, then the angles opposite those sides are congruent. So maybe we'll start with that here. Okay, so the ITT states that the angles opposite what does it say? Two congruent sides, or two sides of a triangle congruent, then the angles opposite those sides are congruent. Well, it states that the angles opposite two congruent sides of a triangle are congruent. So, extending that logic right here, if all three of the sides of a triangle are congruent, then we can apply the ITT twice. And the transitive property, I'm getting kind of ahead of ourselves here. I'll draw a diagram in a second. Intransitive property, to confirm, all three angles would have to be congruent. So here's one where maybe if you're justifying how this follows, where a diagram could be very helpful for you. Here's my answer. Feel free to reread it. Email me if you have any questions or whatever like this. But this is how I would do it, right? Through ITT. If I had a triangle like this, and if I knew that, okay, I have two triangles congruent, so we have triangle A, B, C. And it's given to me that AB equals BC, right? I would use ITT to prove that the opposite angles of those two sides would also have to be congruent to one another, okay? So this is ITT, right? Then I would get angle A congruent to angle C, okay? And that's the ITT right there. So we apply that once. But if it were also given to me that I had side AC is actually equal to BC and equal to BA. And that's the definition of an equilateral triangle. All three sides have the same length, right? Have the same length here. So at this point here, I could say this, right? I could say that length AC would equal length BC, and therefore I can apply the ITT to justify, right? Remember this one single arrow going to the right here means if then. If AC equals BC, and we know it would because it's an equilateral triangle, then angle B would be the same measurement as angle C here. So I'd have angle B congruent to angle C, and then this right here, right? This right here would get us to what we're trying to prove here. It's a really messy diagram here, right? If I know that AB equals BC, then I know that angle A is congruent to angle C. That's the ITT. If I know that AC is congruent to BC, or AC equals BC, then I know through the ITT that angle B is congruent to angle C. And then because I know this, because I know angle A is congruent to angle C and angle B is congruent to angle C, then I'm going to apply the transitive property here. And look at this here, angle C and angle C, they're both congruent to angle A and angle B, right? Angle B. And when two things are each congruent to the same thing, then they are congruent to each other. And that is the transitive property of congruence. So I have trans here for transitivity, and we're going to get angle A is congruent to angle C. And then we've kind of said it all right here. We can kind of say that they are all congruent to each other, and that this would actually be an equilateral triangle here. Okay, so a little bit more in advance here if you were to actually kind of word that one out. That's how I would start this. Well, if we're an equilateral triangle, then AB equals BC. Then angle A would be congruent to angle C because of the ITT. And if we were an equilateral triangle, we'd also know that AC was equal to BC, and then because of the ITT, angle B is congruent to angle C, and then so we applied the ITT twice, and then my transitivity, we would know that angle A is congruent to angle C, and if angle A, I mean, you can apply the transitive property again here. Angle A would also have to be congruent to angle B, right? Because angle A is congruent to angle C, and angle C is congruent to angle B, and they're all congruent to one another. So now we've proven corollary one here. An equilateral triangle also has to be equiangular, okay? You're gonna get the three sides, right? The three sides, they're all the same length. All three of those angles will be congruent to one another. And then your answer for number 11 is gonna be very fast, right? Because if you know you have 180 degrees in a triangle and all three angles have the same measurement, you would just divide by 3, and then each angle would have to measure 60 degrees, okay? So an equilateral triangle has 3 60-degree angles. It's very easy to know that an equiangular triangle had 60-degree angles, but now, right, now that we know an equilateral triangle is also going to be equiangular, those 3 angles are all 60 degrees here, okay? Also going to have to justify number 3. Hints on that one? SAS, SAS, okay? Right, you got to use SAS. All right, let's keep going on here. We got write proofs in 2-column form. Let's do this. Number 6. I don't have the actual proof on here because, reminder, whenever you come across a proof in a problem set, you got to have all 4 things. Okay, 4 things are required anytime you have a complete proof, and it's not required if it's a fill in the blank proof. I think number 5, you're gonna have to do number 5. You're just filling the blank here. Okay, so you don't have to draw the diagram down here. You don't have to write the given and proof statements down here. That's not something I look out for. Not something I have my TA look out for. Okay, because it's all here. These should be a relatively quick problem. You have to be more thoughtful on 6, 8, and that's it for the proof. So 6 and 8 here, because you have 2 big proofs on here. You want to spend maybe about 5 minutes each one. Let's see if Mr. Ford can get done in 5 minutes. I doubt he can, right? Because he talks a lot here. Anyways, the 4 required things you need on a proof, okay? Going back to section 1.8, I've been telling you guys this. You need a diagram. Draw a diagram out. Okay, you need to write the given and proof statements because that's going to help you think about the proof, help you think it through. Finally, last 2 things, statements and reasons. Those 4 things are required for, like if you're writing an essay, you need to have your name on top. You need to have the date. You need to have the formatting correct, right? You need to present it in a way that shows that you're thinking this thing through, okay? Part of the reason why I want you to have the diagram written out and write the given and proof statements is because you're marking up things you know. You're working visually in addition to the written out stuff here. Just watch me do it. I know you've watched me do it 100 times here, but let's watch me do it again here. Okay, so I'm just drawing out we have a bunch of triangles here that I think we're drawing out. It gets a discussion happening with me too when I require you to draw that out here. Okay, so I'm gonna get this. This is angle 1. This is angle 2. This is like, I'm wondering here if that and that, right? Or I don't know. They got two triangles there. I don't know if I'm gonna find congruent triangles. We have parallel lines, perhaps. There's U. There's V. We got R. We got S, and our puzzle begins, my friends. Okay, so angle T is an angle in both triangle RTS and an angle in triangle UTV. That might come into play, okay? So remember that if you have overlapping things, sometimes I just mark it up as being congruent to one another here, okay? So I'm going to mark that congruent. I don't know. Maybe I shouldn't, because I doubt I have congruent triangles in this. Like, this triangle here is obviously smaller than the larger triangle, so I don't know if I have that here. Okay, given we have angle R is congruent to angle S. So I'm going to write this down, but I'm also going to mark it up. Angle R is congruent to angle S, and let's mark it up here. Okay, so it looks like I'm using the ITT at some point. Oh, ITT converse, the converse ITT. So that's my guess here, because I'm given those two. Those are base angles of triangle RTS. If their two angles are congruent, then the two sides would be congruent too. So I might use ITT converse. All right, so you're just thinking through as you're marking up all your given premises, what this might connect to, right? What this might connect to. Angle TUV is congruent to angle TVU. Okay, so you're getting intimately involved with your diagram here. You're getting to know it quite well. And this is TUV, boom, boom. And this is TVU was this, okay? All right, there we go. We got an isosceles triangle here. We're going to have an isosceles triangle here because we're going to prove it's isosceles. Didn't give it to us that it's isosceles, but we can prove it through a few steps here. Okay, so we want to prove that RU has to be equal to SV. So this is a little pesky one here, where I think I might need to use the segment addition postulate. Let's check it out here. All right, structure it out. Right, now we've got it written out here. Statements, reasons, okay? My goal is I want to determine, is this congruent to this, right? SV and RU, are they congruent? Well, let's think about some things here. We have that we can say potentially a little bit later. So in here, they gave you angles. They gave you base angles of a triangle were congruent. So what are you going to use? You're going to use ITT here and use the converse ITT. Which one's the one that starts with angles? So angles isn't an isosceles triangle if they give you two angles. We don't know if it's isosceles or not yet. So it's not going to be the ITT. ITT is the one where you start with the sides, right? You start with the sides because you start with knowing it's an isosceles triangle, okay? Converse of the ITT is if I have two angles that are congruent in triangle, then the sides opposite are going to be congruent, okay? So opposite of angle S in this larger triangle, triangle RTS, is RT, and that would have to be the same length as ST, okay? ST. So I'm going to use the ITT, converse ITT, to prove that that those are the same lengths here. If I know that that is the same length as that, and look here, UVT also has base angles of this triangle are congruent, so that means I can mark this up. 1, 2, 3, 1, 2, 3. So here, the question is this part plus that part equal the whole, right? If I know that part is congruent to that part, and this whole is congruent to that whole, can I prove that that part has to be the same as that part? Well, part plus part equals whole, part plus part equals whole. I'm guessing all these parts are going to correspond and be congruent to one another, right? Those two parts are congruent, those two parts are congruent. So if you're adding equal parts, you should get an equal whole, okay? So remember, going back to section 1, 2, you had some part plus part equals whole assumptions that were made here, and the way that our actual shape should behave in terms of specific lengths or specific angle measurements here, okay? Remember what those are, part plus whole, the part plus whole assumptions? Those were our addition postulates, part plus part equals whole. So segment addition postulate is definitely one you're going to use on this one here, okay? Sometimes it's been a while since you've used the segment addition postulate, so you might have forgotten about it. But let's check it out here, if we can use it here. All right, start with my givens. All right, let's walk it back here. So I'm going to use the converse ITT because my brain's just like, what did I do this previous section here? I want to start by getting some equal things here. We're going to end with equality. I want to start with equality here. So angle R opposite here, I got to do ST is equal to RT. And I'm also going to say that UT is equal to VT. And that's from the converse ITT, right? I started with congruent angles. I end up with congruent sides. Two congruent angles in a triangle, the sides opposite of those, right? Opposite here and opposite here, they're going to be congruent to one another, okay? And I can do that because I have two pairs, right, of base angles here. Base angles of that triangle and base angles of this triangle here, okay? And I got this. Now, I haven't talked, so here's where you can maybe think backwards at this point. I haven't talked about RU yet. How would I talk about RU? How would I talk about SV real quick here? What I can say about this is that I could use the angle addition postulate. That's right, I can use the angle addition postulate here. So what I can do is this, I can use the angle addition part, that RU, okay? I can get RU into the proof by talking about RU plus UT equaling part plus part equals whole equals RT. Okay, that's segment addition postulate. And I can do that for the other large segment here. So the whole is going to equal this part, which is SV. And that's important because SV is part of my last statement. I got to get SV equal to RU at some point, okay? But it's SV plus VT. Those are the two parts that comprise the whole segment ST. So we're talking about distances here because there's no bar on top of it, distance ST here. Segment addition postulate, okay? I know from up top here, right? I know from up top here that ST equals RT. So what I can do is I can replace this in here, okay? I can do a little substitution in here. That equals RT, so that's going to have to go over here, okay? And this is going to have to go over here because RU plus UT equals RT. Put that over there. SV plus VT, that equals ST. Then I'll put that over there. So next part would be substitution. Substitution. And hey, I think we can finish this proof right now. Man, keeping a lot of track in your heads here. So now what I have saying this statement here, I have part plus part equals part plus part. And that's good because I knew the wholes equaled each other. That wasn't exactly given to us. We proved it through the converse ITT. So if I know that part plus part and part plus part, in these two parts here, these two three tick mark ones in purple, they equal each other. I can simply subtract those from both sides, okay? I can subtract those from both sides. Because I know this, UT equals VT, I can subtract VT here and subtract UT. I can subtract equal values from both sides of an equation, and the equality will be preserved. And that is the subtraction property of equality. So we get SV equaling RU, and boom, 5-step proof, we got it done. We got it done, okay? Subtraction property of equality. Only way to get better at proofs is just to do a lot of them, right? And to think critically, right? Follow the form, didn't get it, tear it up, try it again, right? Rewatch this video, okay? And then try it on your own. Try to follow the logic. Let's go into number 8 though, because hey, maybe see a second example that will sort of give you ideas on how to do problems like this here. All right, so this one has to do with XY. XY is right here, XZ is right here. So it's gonna have to do with a different diagram. You're getting involved with the diagrams here. You show that you're reading this and that you're giving yourself a chance. And your diagrams don't have to be perfect. So Mr. Fortin knows his handwriting's not very good. It's not about handwriting, guys. It's not about handwriting. It's about thinking about it, okay? So I try not to make my handwriting be very good because you don't want to get hung up on stuff like that, okay? You want to just keep moving and show you don't have to be a perfectionist, right? And I want to show you guys you don't have to be a perfectionist here. To kind of make sense of this. We just need to move, right? We need to move here, okay? So now I'm going to get point O up top, and I got angle 1. I'll do this. I'll be a little bit more perfectionist here, and I'll actually mark it up in what they have in red. Oops, when they have in red. Oops, they have in red in the diagram here. So this is angle 1. This is angle 2. This is angle 4, and this is angle 3. And we're going to make an argument here. We're going to make an argument on this one here. So I'm guessing that XY probably equals XZ, right? That's an isosceles triangle. I'm guessing this bottom one's an isosceles triangle because, again, this section is called isosceles triangles. So we're probably going to use either the ITT or the converse ITT. I don't know. Let's see. And you guys are going to get a second day of this on Monday and then Tuesday, right? Because we're doing these like 2-day things. Like you get a new lesson, then you do the homework the next day. So anyways, you'll have another day, 2 days, right? 2 days when we get back Monday, Tuesday to keep working on this stuff. But here, diagram written down. Take a deep breath. We've got a diagram down. We're getting to know this a little bit here. It takes a minute to get to know the problem. Right? Don't just say I'm stuck. I didn't get it all. And not have the diagram written down, given proof premises. Because my friend, that means you're not trying. You're not giving yourself a shot. You're not trying hard enough here. Here we go. You want to get this stuff. That's the goal. All right. Anyways, we're given that xy is congruent to xz. I'm marking it up. You better believe I'm marking it up here. What did I mark up here? What color did I use? I used red. I used red to mark up. Okay, I'll stick with that to mark up what's given to me. So I'm starting with xy congruent to xz. That's great. Am I going to probably use the isosceles triangle theorem here, or am I going to use the converse of the isosceles triangle theorem? Well, if we're given two sides of a triangle are congruent, are we given that it's an isosceles triangle? Yeah, that's an isosceles triangle, at least two sides of a triangle being congruent. So my guess is we're going to start with those two triangles congruent, and then we're going to prove that angles are congruent here. And that is the isosceles triangle theorem. That's the ITT. If two sides of a triangle are congruent to one another, then the angles opposite those two sides are congruent. Okay, so when I know that angle XYZ is going to be congruent to angle XZY, right? I'll probably use that. I have my argument here, okay? I'll actually ask you guys if there's an easier way to prove this. I'm gonna do that on Monday, okay? A little hint here, there's actually an easier way to prove this. I'm gonna ask if somebody can do this in fewer steps. We'll get back to this in a second. I like this proof. All right, anyways, I'm gonna prove it the way the book is expecting you to prove it. And then I'm going to reveal on Monday an easier way to prove this here. Here we go. We got OY congruent to OZ. I'll mark that one up here. Just be calm. Be calm getting this guy done here. Boom, 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 boom. Do you see an easier way to prove this? Well, we actually haven't written down the last thing to prove. The thing to prove here. So those are our given premises. This I can say right away. I can use that. Work with it until we get to our proof here. Is measure of angle 1 congruent to measure of angle 4? Well, it's saying, hey, prove it. So my guess is yes. But we don't know it yet. So I'm going to mark it up still. Be like, this is our goal here. Is try angle 1 congruent to angle 4. But I'm going to put a question mark next to it here. And wait a second, is there a really fast way you can prove this? Look at this. Look at this diagram. Say diagrammed it up like this. Is there a really fast way to prove this? All right, presentation opportunity. Let's take it out. Let's take a look at it for 10 more seconds. Really fast way you can prove this without using the ITT. Hint. Let's do something else funny. 5 seconds. All right, presentation opportunity on Monday. If you can do that, then you earn yourself a free late pass, my friend. So yeah, just mark this one up. This one's a cool one. I like this one because there's a faster way to do it. And hint, auxiliary sets. Auxiliary sets. Yes, if you're watching the lesson videos, you know what an auxiliary set is. And a few ways to introduce one to a diagram. All right, anyways, we got statements. We got reasons. Statement number 1. We want to get our given premise into here because, again, the way that proofs kind of work is that they're kind of long if-then statements, right? Eventually, you're going to write things called paragraph proofs, which are just ways of starting with your given premises and your given diagram here. How you can work with that thing to see that necessary things follow from it, knowing all the laws we know here, okay? So if I know that xy is congruent to xz and oy is congruent to segment oz because it's given to me, then I can say, as a next step, okay? So you see, it's just a long if-then statement. If this is true because it's given, then I can do what? What's the thing? If I start with sides being congruent, I could say what are congruent then? I can say angles are congruent. So for instance, I can say that angle XYZ, this is the way the book expects you to prove this, is congruent to angle XZY. Okay, so these holes are congruent because XZ is congruent to XY, and the angles opposite are those large angles, right? They're the whole angles here. So here, I can say what would follow this top premise is that angle XYZ is congruent to angle XZY, and that is the ITT. Ooh, sorry. Yes, the ITT. Ooh, you got to double check yourself. Check yourself before you wreck yourself. We started with sides being congruent. we're ending with angles congruent. Okay, so when you start with an isosceles triangle, that's the ITT, right? Start with sides being congruent. You get angles, ITT right there. Okay, and then the second thing we can confirm is that this is also an isosceles triangle down here. OYZ is also an isosceles triangle because OY is congruent to OZ, and if that's the case, then these angles, which are opposite those two sides in that triangle down here, would also be congruent. Okay, I need to say this. Oh, they number the angles. That would have been easier if I numbered the angles. If I use that, because I don't have to worry about how I properly name those angles here. And using 3 letters, I can just use 1 character, use 1 number here. Okay, angle 2 is congruent to angle 3. That's also the ITT. Started with congruent sides, ended with congruent angles, ITT right here. All right, step 3. So this is going to work very similarly to the last one. Okay, again, there was a faster way to prove this where you could avoid this. But here, the idea of this is this part, right, this part congruent to that part? Well, we know the holes are congruent. This hole, W-H-O-L-E, this hole is congruent to that hole, and that part, the other part here, is congruent to the other part there. So there's only one way possible. This part must be the same as that part because part plus part equals whole, and if the holes are congruent, the other part's congruent, then or equal to each other, then the measurement of this part is going to equal the measurement of that part here. Okay, we got to get done here because remember, this goes back to section 1.3. Section 1.3 was another part plus part equals whole assumption. That this is so super primitively, supremely primitively obvious that if you have a partial angle, well, not a partial angle, if you have an angle plus another angle that makes up a large angle, so we call that a part plus part equals whole relationship, that is an assumption that part plus part would equal the whole, which is the what assumption? Assumption's postulate, right? We're adding, so it's an addition postulate of some sort. It is the angle. We're adding angles here. It's the angle addition postulate. So this is the angle addition postulate. Okay? We know it takes some time for you guys to start getting good at proofs. So this is like a reminder, right? We didn't think everybody would get it in chapter 1. Didn't think everybody would get it in chapter 2. Hopefully most people get this in chapter 3. Why this next statement is the angle addition postulate. Because what I'm going to say is part plus measure of angle part, so measure of angle 2, equals the whole, which is measure of angle XYZ. Okay, so I actually did have to name it that way because this is an unnumbered angle, but we know measure of angle XYZ equals measure of angle XZY, and that's what I'm going to do next. Is I'm going to do this part plus that part equals this whole, so I'm going to do this part plus this part equals the whole here. Okay, so measure of angle 4 plus measure of angle 3 equals measure of angle XZY. Okay, I'm going to change this here to the ITT. Instead of doing the 2 congruent angles, I'm going to say the 2 angles measure the same, okay, because of the ITT. We're allowed to do this. And I'm going to do that also with this one here. This is a little bit like, usually try to be consistent in problems like this. If you're talking about measurements, it's better. So try to talk about measurements better because then you can use the addition postulates. You can add measurements together. You can't actually add congruent shapes together. It doesn't make sense adding a shape to another shape. Measurements are numbers. Shapes are just shapes, right? We don't add shapes together, okay? So anyways, I just changed that here. Note I just changed this here to equality, and I put an M in front here because now I can work with this. I can work with my angle addition postulates here. Okie doke. What do I have here? Measure of angle XYZ. This whole equals the other whole. Right? We knew that from the ITT. So what we can do is we can, again, the same thing we did in the last problem. We can take this. We can take, why did that erase? No, I don't want that to erase. My measurement's erased here. Okay. So I got my measurement here. I got my measurement here. Oops. And good. I got my circle thing erasing. I want to take this thing and replace this because it equals it, right? It equals measure of angle XYZ. I want to take this and replace measure of angle XZY. I missed the Z here because that's what I see right here. And so again, I'm going to do substitution. These proofs are almost this one here and this one here, almost exactly the same here. Okay, so this is step 4 is measure of angle 1 plus measure of angle 2 equals measure of angle 4 plus measure of angle 3, and here I get messy, right? Math can be messy, right? But as long as you're organizing in your head, right, that's the ultimate goal. It doesn't need to be pretty, right? Just needs to be logical, okay? And this is the substitution property. Okay, because what we're doing is we're substituting this into here, right? Because it equals it. We're taking this, we're substituting that into step 2 because it equals x, c, y is here and it's here. Look at that, it's in the same places. So what if one thing equals another thing, it can be replace that thing in another equation, okay? So now I have this substitution. Step 5, I can finish solving this one now. I can solve this and deduce that measure of angle 1, this part had to equal the same measurement as that part there because I'm going to subtract the other parts from this. I can subtract measure of angle 2 from the left side here, right? Because I got this. I'm going to change that in different colors so we can see it. If you didn't see it a few chapters ago, hopefully you see it now. This is here. I'm going to subtract measure of angle 2 from the left side of the equation, and I'm going to subtract measure of angle 3 from the right side of the equation because they equal each other. Remember, when you have an equation, you're allowed to subtract equal quantities on both sides of the equations, and the resulting equation will be preserve that equality here. You have a scale here, right? You take this one thing off of one side, you take the same thing off the other sides or equal thing off the other sides, you end up with a balanced scale, right? Equality is preserved here. And that's going to allow us to arrive at our answer. Measure of angle 1 equals measure of angle 4. And that is by the, oops, it means insert text box yet again. That is by subtraction property. Why? Subtraction, BOE. All right, 2 5-step proofs right there. This one here, you can get done faster than 5 proofs. It's possible, and we'll review that on Monday. I'll give you a presentation opportunity here. All right, solve for x and y. It's a little bit tricky here, but got a little algebra problem snuck in. Probably on Monday, you'll have a few more algebra problems on this one related to geometry right here. We got an equilateral triangle, my friends. Well, it's going to be equilateral because it's equiangular. So this is just making sure you know that corollary, the final corollary that you have in this lesson, that if you have an equiangular triangle, okay, an equiangular triangle is also what? It's got to be equilateral because all 3 angles equal the same thing. Applying the converse ITT twice, opposite of those 2 angles means those 2 sides are going to be congruent, and opposite of these 2 angles means this side and this side would be congruent. And then all 3 sides would have to be equal to each other, okay? So an equiangular triangle is equilateral. That is the 6th theorem that you learned today in this lesson, and it's the corollary that follows from the converse ITT. Because here you use converse ITT first to say that was congruent to that, and converse ITT second to say that that was congruent to that. Okay, so now we have this. I can mark it up if I want to. Let's just make this A, B, C. And AB would be represented as the quantity, because it's variables here. They want you to practice some algebra right now. 4x minus y, that's that distance here. Again, we have some variables listed here. It's going to somehow express how long this has to be right here. BC is going to be 2x plus 3y. And AC equals 7, okay? So we know that the perimeter of this, for instance, is 21, right? That might help you at some point. I don't know if it does or not. But what I do know is that I know that 2x plus 3y equals 7. Okay, I know that, for instance, here. I also know that 4x minus y equals 7 as well. Okay, so in Algebra 1, I haven't covered how to solve a system yet. That's actually my first unit, second semester. I know some teachers try to teach it first semester. I always teach it first semester, but this is a weird year right now. I'm doing 3 chapters, not 4 or 5. Not 5, let's be honest here. I haven't gotten to solving systems right now yet. But for those of you who took Algebra 1 last year, this should look pretty familiar, right? Should look pretty familiar because this is a system, okay? System of equations. And again, what a system of equations is when you have 2 equations, right? We got an equal sign, so we know it's an equation where they share the same variables, right? And we got to find common solutions, right? The same x's and y combination should work in the top equation that work in the bottom equation. What are the common solutions to these ones here? Let's figure this out here, okay? There are a few ways you can solve this one. If you know the elimination method, I think that's probably the easiest. I'm not going to review that because I think that's like probably the most confusing. We're not in geometry, we're not solving by eliminating much, but we are solving by substitution. Okay, so we're going to do some algebraic manipulating here that I'd recommend if you really struggle with solving a system like this, is I'd recommend to solve the system by the substitution method. Okay, by the substitution method. So remember, if I know one thing is equal to another thing, I can use that other thing to replace something in the original equation. So anyways, the way I would do this here is maybe to change this one around to isolate y. Okay, we're going to isolate y, get y by itself, and then we're going to substitute it into the top equation. Okay, you'll see what I'm talking about in a second here. Okay, so I'm going to ignore this top equation. I'm going to isolate y. The way I would do that is I would add y to both sides. Okay, then I'd have y plus 7 over here. I'm also going to subtract 7 from both sides. Okay, so I'm going to change this. 7 minus 7 is 0. And 0 plus y is y on the right side. And here, negative y plus y is 0, right? So I'm trying to isolate y. I want to get y out of the side here. Now y is over here. Now I got here 4x minus 7 is equal to y, okay? So this is a valid statement right here. If you're like totally lost on this, like why I would just do something like this, okay, well, keep watching, but maybe you want to meet with me when we get back so we can just practice some substitution problems. If you're just like, listen, I took Algebra 1, I really didn't get that in Algebra 1, I can help you. I can meet with you and go over it, okay? Unlikely you're going to get a substitution problem like this or a systems problem like this on a test, because I know that I have some 9th graders in geometry class here, and this hasn't been covered for all 9th graders yet, but I'm hoping you've seen stuff like this at the very least so far. Okay, I have this. This is important because now I can take this and I have a y up here. Okay, I have a y in this top equation. Now I'm thinking about equation number 1 here. This is equation number 1. This is equation number 2. I just manipulated equation 2 to become this. Okay, become this right here. Why is that important? Well, I can take what y is equal to and replace y in the other equation. Okay, why couldn't I have solved for x and y this top equation originally? Well, I had an x, I had a y. We can't figure out what they're equal to because we have x and y in the same equation. So if I know what that y, because I manipulated this second one here, if I knew that y was equal to this, I can just replace that y with this expression that where x is my only variable in this here. Okay, so what I'm doing is I'm rewriting equation number 1, kind of using the way I rewrote equation number 2 in here by substituting in the value of y here for what I know y, an expression that I know y must be equal to, because I changed around equation number 2 here. Okay, and then I'm going to bring down the 7, and this is a little bit of a preview of the substitution method. If you haven't done this in Algebra 1, don't worry about it too much. But if you haven't done this in Algebra 1, maybe you want to meet with me to get some help on this here. Because again, we're definitely not going to have time to go over this this year in geometry here. So anyways, 3 times 4x is 12x. 3 times negative 7 is negative 21. And then this is 7 here. So now I only have x's in my equation. So I took what y was equal to, replace y. I only have x's in my equation. I can solve this one now, okay? So I get here 2x plus 12x is 14x. Negative 21 plus 7 would bring us to 28. Divide both sides by 14. X is going to equal 2, okay? X is going to equal 2. And if I go back to my original equation, or one of these two equations here, and I'm going to choose equation number 1. Let me bring this one down here. And x is 2, so I can just replace x, right, with 2, and now I can solve for y. Okay, going through this a little bit quickly, but this video has been long enough here. Okay, this is 4, and plus 3y equals 7, so I'm going to maybe just subtract 4 from both sides. 7 minus 4 is 3, and I got 1 for y. Okay, y equals 1, x equals 2. And there you have it. There you have it here. Okay, what was the last one that I said I was going to do? If you're looking to get into detail, right? We did classroom exercise number 10. I told you about the other ones here to let you think about them. Written exercise 6, 8, 20. Ooh, 28. 28. Let's check it out. 28. Let's check out 28 here. Let's check it out here. Let's get into it here. Number 28. Wait a second. Wait, this is pointing to me or pointing to you? This is pointing right at you right here. Look at that. Let me erase it here. Oh, we got a finger pointing at us. Uh-oh. Does that mean Mr. Fortin's going to go over this problem? No, he's not. No, he's not. Mr. Fortin is not going to go over this one. I tricked you. Watch the whole video just for number 28. Nope. Sorry, folks. Do not pass go. Do not collect $200. You need the homework late pass, friends, because somebody is going to explain this one. Not everybody's going to get the homework late pass. It's just the person to explain this one. So anyways, if you crack the code on this one, you're going to present on Monday to the class. And remember, when you do that, you earn a free late pass for a future homework where it's just like you're tired. I'm not going to do this. It's too much geometry garbage. I don't want to waste an hour of my night doing another geometry problem set. Okay, cool. Take another day or two. Free late pass. You don't get anything docked, nothing like that. So here, not going to go over this one with you because one of your teammates will explain it to you. It's not just about listening to me, learning how to listen to a teacher. It's learning to listen to each other, work with each other. That's right. Anyways, if you're dying to figure out this one and learn how to do it, hints on this one. Can you figure out the sum of the measures of all these angles here and all these angles here? How does that help you? How does the isosceles, step 2, can you figure out what this angle measurement equals, what this angle measurement equals, what this angle measurement equals? So meaning, can you figure out what one interior angle of this polygon here and this polygon here measures? And then step 3, how can the isosceles triangle theorem help you on this one here? Okay, that's my hint to you. This is a C-level problem. I don't think this one's too crazy here. I think some people will be able to crack the code on this one, but it is a C-level problem. Just want to give you a fun one at the end to ponder, to think about, to let simmer a little bit here over your Thanksgiving week. All right, anyways, if you watch this video because you're missing your Mr. Fortin fix, well, hey, I'm glad to give you that Mr. Fortin fix. Thank you for all your effort and for trying this stuff out here. It is really exciting when you can crack the code in this stuff, and I look forward to when we get back in December, helping you crack the code on this strange world of geometry on yourselves. Have a great rest of your break. I will see you guys in December. Bye. December or November 3rd? I don't know. Who knows? Sometime at some place. Bye.